Software Engineering Radio Episode 78, Fault Tolerance with Bob Hanmer Part 2. Hello everybody, this is the second part of the fault tolerance discussion with Bob Hanmer. The first part obviously was last episode, 10 days ago. So if you haven't heard the previous episode on fault tolerance, you should really go back and listen to that first. In the previous episode, we discussed a number of terms we're using here, like reliability, availability, fault, error, failure. We talked a little bit about the fault tolerance mindset, about how to build systems, keep it simple, quality versus fault tolerance and stuff. We talked a little bit about the shared context in which all of those patterns reside. And then we had a little overview over all the patterns and over how this episode is structured and stuff. And we started with discussing architectural patterns. In this episode, we're going to continue with the detection patterns and then also look at error recovery patterns, error mitigation patterns, fault treatment patterns, and then a discussion at the end about designing with the patterns and why Bob wrote the book. So again, if you didn't listen to the previous episode, go back, do it. Otherwise, this one probably won't make sense. Okay, so here we go. Have fun. Let's look at the second bunch of patterns, which is the error detection patterns, or actually generally the detection patterns. It can be faults or errors, I guess. So let's start with fault correlation.
Fault correlation is a pattern that relates to, you've got these error reports that are going into the fault observer, and you'd like to know what it is that went wrong. Mm-hmm. So you want to know what the fault is. And so fault correlation is the thing that's looking to see, have I seen this kind of error before? This error signature, do I know that this means that we had a bad message that we received, or do I know that this means that we have corrupt memory somehow? And so we're taking, fault correlation is taking the detection report, some part of the system detected a problem, and fault correlation is classifying it, deciding which bucket it belongs in, because each of those buckets probably has a different set of techniques to be used to help resolve the problem.
Okay. And the next one, error containment barrier, sounds a bit like the firewall we've been talking before.
Yes, it is. It's the firewall, and it points right back to units of mitigation. Yep. The point here is that you want to confine the error. You detect it, and the first thing that you need to do in a fault-tolerant system is to isolate the error. And isolate in the firewall sense. Cut it off from the rest of the system so it can't propagate. And error containment barrier is telling you to do just that.
Okay. How do errors spread generally? It means, for example, you have some bad data that is then used or that's passed to another subsystem, to another error unit of mitigation, and that would mean that this other unit would also fail because it now works with the faulty data, and that's basically what you want to prevent, right?
Yes, exactly.
Okay.
Isolation is a really, really important thing, and it's really, really system-specific and unit of mitigation specific. So it's really hard to come up with generic patterns on how to do the isolation because it is so context-specific.
But one way of doing that, and that's, as it happens, the next pattern, is probably to check very carefully, and not just syntactically, but also in some sense semantically, the parameters that are, for example, passed in an operations call in another unit of mitigation, right?
Right. Complete parameter checking is the pattern, and it would argue that you should check, every return code and make sure that it's correct, that you should check the value, in addition to checking the return code, you should also check that the returned values are correct or within the correct range, that kind of thing. This is really similar to programming by contract.
Yeah, I was about to ask that, yeah. So is contracts or this kind of DBC stuff a la Eiffel, is that used in these kinds of systems, or is it basically, just manual if statements in all those places that are used to check these things?
From the systems I've seen, it's been manually done with if statements rather than any kind of larger framework. And part of the reason goes back to predating the design by contract.
Yeah.
And then part of it goes back to keeping it simple.
Yeah.
That's extra. If you've got a framework to help you do that kind of thing, that's extra infrastructure that could have failures.
And nobody's using Eiffel, which would provide language support, but I guess that's out of the question anyway.
Right.
Okay, the next bunch of patterns are more or less related to monitoring the system. System monitor versus watchdog versus heartbeat. They all sound relatively similar to me.
Yes. And they work together very, very closely. System monitor is kind of the higher level pattern. It's saying to create some part of the system that will watch the important things. So there are some things in your system that really have to always happen. And the system monitor is saying, okay, set up something that is going to monitor that. And then how does it do it? Gets to watchdog and heartbeat. And I'll go about heartbeat first. Heartbeat, the typical heartbeat message. Sending a ping, sending a message from one place to another and waiting for the response. And if the response doesn't come quickly enough, assuming that the other one's in trouble, or if it comes garbled, assuming the other one's in trouble. And that can go either way. It could be, are you okay? Oh yeah, I'm okay. Or it could be a periodic, I'm okay, I'm okay. So it works both ways.
Yeah.
In order to do a heartbeat, you really have to put something into the system because it needs to know that it needs to send the heartbeat or acknowledge the heartbeat.
Yep.
And there are some cases where you just can't do that. And that gets to the watchdog pattern. And watchdog is a really good pattern. Michael Pont has some excellent versions of it.
Yeah.
And it's a really rich area, so there are lots of watchdog patterns. And typically you think of it as being like a watchdog processor, a little timer that's doing the watchdogging. But you could also put in the software structures to have a third party monitor that messages were flowing between the first and second party and use that information to determine whether they were operating correctly. And by doing that, you haven't modified the first two.
Sure, yeah.
So you're watching it from afar.
Watchdog relies on existing message flow and information, whereas the heartbeat relies on specific messages that are built in the system specifically for that.
Exactly.
Okay.
There's a pattern, realistic thresholds, that discusses how you would pick the appropriate threshold values to use with the heartbeats and so on. Right,
because if you have too much of that, it probably deteriorates the system performance.
Yes, it gets to system performance, or you might think that there's a fault too often or not often enough. So there's some things to think about, and so that's included in here.
Yeah. So that leads us to the metrics, I guess, to detect resource acquisition problems based on existing metrics and experience, I guess.
Yes. We talked about performance in the introduction, and there probably are system performance requirements on how the system should perform under different workloads. And if the system is getting too many workloads, and in the telephone network case, we talk about events like a hurricane or an earthquake, and everybody wants to call their friends, or that new soccer match, everybody wants to dial in for those tickets. And that's the worst time to be adding extra workload to the system to tell you that you're in an overload.
Yeah.
You want to use existing metrics. You want to use things that are really easy to compute, really simple, and that already exist, because when you need this information about overloads and performance problems the most is when you have the least amount of resources to spend computing things.
Yeah, good point. The next two patterns are checksumming and voting. I know what the first one is. I don't know what the second one is. So why don't you elaborate the differences?
Okay. It's interesting, Marcus, because I've never really thought of these two as being that closely related. So it's interesting, and every time I look at this, I learn something new. So the checksum is the traditional checksum.
Yeah.
Compute some value that will tell you that the value that you computed from is correct.
Yep.
Voting is used in cases where you might have multiple redundant elements operating, and you need to decide which of these values you're going to believe. So you get two redundant processors computing a result, which one's correct? And so voting is a method, provides some techniques to use to help you determine which is the correct result when given multiple results.
Okay, the next two or three patterns, I guess, are again related to humans or let's say external observers. They are routine maintenance, exercises, and audits.
And these are related to humans, as you said, but they also can be automated.
Mm-hmm.
And the whole point of these is, no system should be designed to be, busy 100% of the time. So there's always some idle time. And so during that idle time, do some routine maintenance check, and they could be cleaning stuff up like garbage collection, or it could be running the correcting audits to make sure that the data is correct. Routine exercises is a specific case where you've got an active and a standby, and you want to make sure that the standby will work when you need it to. And these can all be triggered by humans, or they could also, be triggered automatically.
Mm-hmm. Okay. The next two, I guess, are probably also related: writing over transients and leaky bucket counter. In both cases, I think that the problem is that you don't want to be disturbed by, spurious errors, I guess, things that go away automatically or from without doing anything, right?
Right.
And then what's the difference between the two?
Well, writing over transient is the bigger pattern, and it's telling you just what you said, that you don't want to waste time dealing with problems that will clear up automatically.
Mm-hmm.
And leaky bucket counter is a really classic technique for actually implementing a counter to determine if a problem that's an error that you're detecting is happening often enough that it should be treated rather than so seldom that you can ignore it.
Mm-hmm. And the way you do this is literally by decrementing the counter with a specific speed, basically. And then if the increase because of the error is getting bigger, then you run over a threshold and then you raise the alarm, right?
Yes, and the perfect illustration is a bucket with a hole at the bottom.
Right, exactly. It's always nice if patterns have real-world analogies that you can visually picture.
Yep.
Okay. So that concludes the section on detection patterns. Now that we know what the fault is, or what the failure is, what the problem, what the error is, we can now try to recover some of these things. So one of the ways for doing that is, of course, if we try to contain the fault to a specific unit of mitigation that already, it sounds like a quarantine, right?
Yes.
So that's the first pattern here. And
the first of the error recovery patterns, these are the patterns, again, that are going to take you to a new state.
Mm-hmm.
In the system, so move the program counter. But the first pattern here is quarantine. Again, putting those boundaries up to isolate, because you want to isolate the error so that it doesn't propagate.
Okay.
And the quarantine pattern is pretty much just a reminder that you want to do that isolation quickly
before it creates much harm. The next one is concentrated recovery. What does that mean? Putting all your system resources to try to solve the problem?
Well, yes, it could be putting all your system resources to try to solve the problem, or it could be just that all the resources you put towards solving the problem, you dedicate them exclusively to solving the problem.
Mm-hmm.
Because if you continue trying to receive and process new requests for service, for example, everything's going to take longer. Those requests for service are going to take longer because there's the recovery going on in the background, and the recovery is going to take longer. And so concentrated recovery is advocating, forget about the new requests for service while you're doing the recovery. Just go ahead and, do the recovery as fast as you can.
Mm-hmm. Okay. It sounds a bit counterintuitive to some extent. I mean, because during that time, your system is not available.
Yes, but And it gets to the different kinds of reliability and availability requirements the system might have.
Mm-hmm.
Sometimes some systems are measured based upon total system availability, and other times they're only given requirements about partial system availability. So you have to trade that off. And again, these patterns have to be customized for your precise situation, because sometimes, as long as you can let a little bit of traffic or workload, dribble through the system, flow through the system slowly, then you're okay and you aren't unavailable.
Mm-hmm.
but in other cases, that's not the way things are counted.
Mm-hmm.
But again, it may not be the whole system. In a multiprocessor or multiple cores, maybe you dedicate one core to doing the recovery and the other three continue.
Yeah.
But on that one that's doing the recovery, you don't do any other work.
Mm-hmm. The next one is error handler, which is probably a bit more than a simple try-catch block, I guess.
Right. The point of error handler, it's concentrating some of the error handling code into one place, which on the one hand increases the complexity slightly because now you have to transfer somewhere and you have to take enough context with it so that you can know what you're fixing. Yeah. But on the other hand, you've concentrated that code and so you can get the faults out of it. And also it's only one place to change when you discover you have a new strategy or you need to try something different. Only one place to change and you don't forget about other places. And so there's a balancing act here, and the pattern tries to point out some of the things to consider about having a separate error handler versus putting it in line.
Mm-hmm. Okay. So that's a relatively low-level implementation pattern, I guess.
One of the lower-level ones, yes.
Okay.
But so people don't get confused. None of these patterns really go to the level of coding. These are all design and architecture level, so there's still a lot of specific design stuff you have to do based upon these.
Yeah. So the next one is restart. So that basically just means if something goes wrong, shut down the system and restart it again?
Yes. Sometimes that's what you need to do. We try to avoid that because it takes a long time to do the restart, but sometimes, that's the best way. And that typically only occurs at the end of a sequence of escalation. We've tried a number of things, and none of them have worked. And so, okay, now we'll bring out the big gun and we'll do a restart.
Yeah. There are several smaller or earlier or less escalated approaches: rollback, roll forward, and return to reference point. What's the relationship between these three and what do they do?
Rollback is kind of the typical thing that we encounter an error and now we're going to roll back and retry.
Yeah.
And maybe we have to restore from checkpoint, which we'll come to in a couple of minutes, but we've gone to a previous state and we're going to retry. Roll forward is for those cases where you don't need to or it's inappropriate to roll back and retry. And so actually roll forward is, we're in the middle of this transaction, we've gotten an error, we'll just discard the rest of it and we'll go on to the next one. Mm-hmm. That kind of thing. Return to reference point is very closely related to these two, but it is more intended for the non-main application leg code. So you're doing a correcting audit, for example, and which isn't arguably the main application function of processing telephone calls or web requests or anything. Yep. And you've got an error in there. Where do you go from there? And so return to reference point is getting the system synchronized again, because you may not need to roll back. If an audit has an error, you might want to just restart normal execution. I don't mean the restart pattern. Mm-hmm. You might want to resume the normal execution, and forget about the error happening. Mm-hmm. So rollback and roll forward are basically for the main application. Return to reference point is for the maintenance code, if you will, and restart is like the whole system if you've got a big problem.
And rollback is basically retry, whereas roll forward is ignore.
Yes.
Okay. So if you retry, there is probably always the trade-off, as in the heartbeat area, that you have to trade off the number of limits you retry, the number of times you retry the retries. If you try too often, then your system might get stuck with retrying old crap that never is going to work.
Exactly, and it was an important enough concept that I included the pattern limit retries in here to remind you to put some threshold, some limit on how many times you're going to retry. Yeah. And this is exactly where someone in charge, that pattern from the architecture chapter, comes to play, because it's that someone in charge that is going to be the one to say, okay, we've had enough retries, now it's time to escalate. Mm-hmm.
Yeah, right. That was a good point. What do you do if you've reached that limit? You escalate to some other strategy, which might then be, for example, roll forward or restart.
Yes.
Okay. The next one is failover. I thought that was a relatively general term. How does that fit into these more or less specific strategies here?
Well, we had redundancy in the architecture chapter, and so failover is a really important concept with regard to redundancy, and so I thought I needed to include it.
Mm-hmm.
And it's exactly what you thought it was. Failing over, we've got one that has stopped working, and we fail over to the other one of a redundant pair or redundant set and resume execution there.
Yeah.
And it's not strictly a hardware concept.
Mm-hmm.
So there's some ideas in this pattern about doing it with software.
Yeah. Okay, and the last one for this section or chapter is checkpoint, which is probably important if you want to be able to return to a reference point or roll back something.
Right.
You already mentioned it before, by the way.
Yes, we've mentioned it before. I mean, this is a really important concept, and this is one of those things that I'm sure people will pick up the book and immediately say, oh, yes, okay, he's got a lot about checkpointing. There have been whole books written on checkpointing also. Mm-hmm. It's a very important concept, and the patterns, it's again a little set, kind of like some of the others we've seen. So checkpointing is explaining a little bit about how storing state information away can help you recover faster. Mm-hmm. But then there's some open questions at the end of it, like what is it that you're supposed to save? What's the best information to save in the checkpoints? Mm-hmm. And then where do you store the checkpoints? Yeah. And so, that could be a lot of different things. And then there's another pattern too. When do you do the checkpoint? Do you always do it well, how often should you do it? Yeah. Who decides when it's time to do it? And so these are all covered in other patterns within this error recovery chapter.
Yeah. Okay. As a usual trade-off, again, if you checkpoint too often, then the overhead of creating the checkpoint is too big, and if you do it too seldomly, you have to go too big. The stuff you have lost is going to be too much. So, yes, a lot of trade-offs to be made.
There are, and so I hope these patterns will be useful to the reader to remind them about all these things they have to consider and trade off.
Sure, but one thing that you need in order to be able to make these trade-offs is a good set of specific requirements, and I would guess that many of the people who do not work in these like safety critical or fault tolerance required areas like you do, they haven't seen many of these specific requirements, specifically if we talk about non-functional requirements. Just always, the system must be available and must be fast. You can't make these trade-offs if you don't know any more specifics.
That you're absolutely right. It's important to get those requirements, or without a specification or a requirement, you can't have a failure.
Yeah, you're right. That goes back to that point, which is also practical. If you can't fail, also a good situation to be in.
Yep.
Okay, let's look at the error mitigation patterns, and they are different from the error recovery patterns, again, in what sense?
Well, the error recovery patterns are the ones that move you to another state.
Right.
So we've rolled back to a different state. Basically, in a really low level, we've changed the program counter in some way.
Yeah.
But there are many situations, and especially performance-related problems, overloads, where we don't change the state. We can do something here locally, that will allow us to continue execution, but we've mitigated the error. So these are in the chapter on error mitigation. Mm-hmm. So we've done something to make the world better, but we haven't changed the state.
Okay, so the first pattern in this section is overload toolboxes. What's that about?
So overload toolboxes, I mentioned this a long time ago also in the introduction, that or in relation to fault correlation, that there are different kinds of techniques that you'll use to resolve different kinds of problems. And overload toolboxes is pointing out that you might have different tools to deal with overloads in terms of memory. You're running out of memory for the application, however that might happen. Mm-hmm. You're running out of tangible resources, maybe network ports or peripheral equipment, or your CPU time is going high, but it's going to be different techniques for each to help resolve overloads of each of those different areas. And so you need multiple toolboxes to deal with those different kinds of problems.
Mm-hmm. Okay.
It's a classic case of, the old joke that when the only tool you have is a hammer, everything looks like a nail.
Okay, yeah.
And this is trying to remind you that no, there isn't one single solution that's going to work with all these different overloads.
Okay. So then let's look at a couple of these solutions. The first one that I see here is deferrable work. So basically, whenever you can do something later, do it later. My principle in life.
Yeah, that's basically right. We talked about the routine maintenance kinds of tasks. Yeah. Those are easily deferrable. If the system's in overload, it must be working pretty well already. Yeah. If it doesn't have other errors, so defer some of that work that would check if it's working okay.
Although the overload might be a consequence of some fault somewhere else, because, for example, something isn't dequeued after it has been processed, so the same thing is processed over and over and over again.
Yes.
Bad luck.
And that gets to another pattern, reassess overload decision, which is reminding you to have the system periodically check that it's applying the correct techniques, because there might be more information to tell you exactly what you said, that it's a fault and you're not dequeuing something rather than an overload.
Since we talked about queues, the next thing to do to mitigate overload situations is queue for resources. What does that mean?
Sometimes you can get away with queuing requests as they come in to process them a little later, because it might be a very momentary spike, or it'll also smooth the arrival rate to the point where the processor will be able to handle it more efficiently. But you have to be sure to do it equitably so that everybody receives good service in some way. And again, the requirements should specify what good service is.
Next one is shed load.
Right. Sometimes you just get too much work in and you need to get rid of it. And so you need to design the system and know in advance how you're going to do that, how you're going to discard those requests that come in that you can't process right now. Ignoring deadlines, just discarding things off the queue, not putting things onto the queue in the first place, are some examples of the way you might shed load. And when you're shedding load, you want to do that very efficiently, because you're doing it in a period of overload. So you want to really be efficient in the way you do it, and not have errors occur during that discarding.
Yeah.
And so, final handling is another pattern that talks about that kind of stuff.
Okay. And if you can't shed the load, you might share it with some other component of the system as an alternative.
Right. Again, the patterns can be applied at design time, so you can think about that. What other processes are in the complex that you're building, or other cores that are doing different kinds of work that you can start allocating resources from when you get to a period of overload. And it could be local, like I mentioned, processor cores, or it could be across a network that all of a sudden you start sending requests to different places. And these are examples of ways of expanding the possible ways of resolving the problem, of expanding the resources, so it's an expansive automatic control.
And then another way is, of course, instead of shedding or sharing, just doing everything a little bit slower, I guess.
Right, just slow it down. Just because by doing that, you keep the system sane, you are limiting what you're doing. You're shedding some work and you're processing what you can, but you're conscious about accepting only as much work as the system can process at any given moment. And therefore, you're going to keep it out of an overload situation that could lead to a failure, or keep it out of an overload situation that is unrecoverable.
The next two patterns are fresh work before stale and finished work in progress. How do they relate?
So both of these patterns, fresh work before stale and finished work in progress, are related to the queuing. Fresh work before stale, in some situations, especially where there are humans on the other end, like of the telephone or of a web request, they get impatient. If the thing doesn't happen fast enough, they're going to resubmit it. And so it's possible in some situations to get multiple requests that are identical in the queue because the person has resubmitted them. And so you want to take fresh work before stale, so you get the most recent request. And then by the time you get to the old request, you'll have some indication that it should definitely be ignored. Finished work in progress deals with transactions that must complete, and maybe the things that are long-lived. And so, there might be a lot of messages that get received, or the system has significant work time invested in seeing that they complete. And so you want to do what you can to make sure that they're allowed to complete, and maybe defer some new work requests to allow the continuation of these others already in the system.
Mm-hmm. This fresh work before stale is something that's probably used in many telephone systems, I guess, because I've had that experience. If I try to call some whatever call center and I don't get through, I just hang up and try again, and now I can get through. So it seems like that's something that's used quite a bit.
Yes, it's a very common thing. And some of these patterns in this chapter, particularly like fresh work before stale and finish work in progress, were first written in pattern form by Gerard Mazzaros, who worked for another telecom company. And so this is building upon lots of good telecom experience in some of these overload handling techniques.
Marked data is the next pattern. Sounds a bit like... Yeah, go ahead.
No, I'm sorry. You say what you were going to...
No, I was just going to say that it sounds a bit like checksum, that you somehow mark data with some properties so you can check whether it's correct, but I'm not sure if that's appropriate.
No, it's the next one after this. Error correction code is like that.
Right.
It's error correction code is giving some redundant information so that you can reconstruct the correct value if for example, the checksum says it's incorrect.
Yeah.
But marked data is a little different. It's sort of like the IEEE not a number standard, or Ward Cunningham had a pattern that was related to, and you've got a data value, it's incorrect, you know it's incorrect, you can't figure out what it should be made equal to, so the correcting audit can't correct it. So instead of that, you put a flag on it that lets everyone know, this value isn't correct, don't use it. But then you let that data value and its flag ripple through the system, and the system just respond, oh, I can't use that value.
That might mean, if you want to use this mechanism in a system, that instead of just using an integer somewhere, you might use a struct that holds the int as well as some kind of markup, some kind of confidence value or whatever, which in turn might be a performance hit. So is it fair to say that in reliable systems, in fault-tolerant systems, you might be willing, or you will have to take that performance hit, that performance overhead or memory overhead, to get the benefit in reliability?
Yes, that's going to be true, that there are going to be extra overheads in memory and processor time associated with being fault tolerant. Those are mitigated a little bit by the fact that we want to keep it simple.
Yeah.
But you're very true that you're going to have to trade some resources off.
So the cost aspect you talked about before, fault tolerance is not free, wasn't just about the money or the effort you put into designing the system. It's also that you have to tolerate certain runtime overhead to be able to detect and monitor the system and the faults and the errors.
That's correct.
Kind of obvious now that I think about it. Okay, that concludes the error mitigation pattern section, and that leads us to the last pattern section, which is about fault treatment. So this is about looking at the root cause and solving the real problem, right?
Yes. In real time, the system has detected the error or fault, hopefully before it became a failure, and we've done the recovery or mitigation steps. The system's back operating normally, and now it's time to really fix the fault. Correct that misplaced comma.
Yeah.
And so these are some patterns that do that, to help you do that.
Okay, but they don't happen automatically at runtime. There is something that's more or less, again, process stuff. What do you manually do? How do you release the next version of the software or something like that?
Yes.
Okay, so let's look at the first of the pattern. It's called Let Sleeping Dogs Lie. Sounds nice.
Yes, and I don't know if this is an expression that translates well, and if it's a common thing that you've heard before.
Well, it's a bit different in German. It's called Wecke keine schlafenden Hunde, which means don't wake sleeping dogs up. But it's kind of simple.
Okay, and I've heard that before. Yeah. So, and the point is that there might be some faults in the system that aren't worth fixing. It's better to leave this fault there, even though they might cause an error again, than to fix it, because maybe the fix would have to be really, really complicated. And so if it's really complicated, you risk screwing it up and introducing more faults. Or maybe it's in functionality that is really used seldom, so it's not worth the effort to actually make the correction because it's going to be such a low probability event. So Let Sleeping Dogs Die is meant to point out to the reader that just because there's a fault, you should think about whether you want to fix it.
But of course, that's only true if you have a system that is fault tolerant, i.e. it doesn't completely fail as a consequence of that fault.
Exactly.
Okay, that's an important thing. It's not about recommending not to fix bugs. You should only not fix those bugs if they aren't going to result in a serious problem.
Right. You need to do the cost-benefit analysis of the cost of fixing it and the risk of fixing it and the benefit of fixing it, and weigh all that together.
Yeah. Next one is reintegration.
And reintegration is discussing when you are actually making the fix, when you're putting it in, that you should have some predefined process or method to actually put it in. You shouldn't just go in and start typing and assume that it'll work the same every time. So write down how you're going to do it. Develop a procedure. And this is partly because a concept that we didn't talk about earlier is that experience has shown that failures in systems are related to either the hardware, the software, or we call it a procedural error, so something a human did. And so you want to have a procedure, a process for someone to follow so we can reduce the number of those procedural errors.
Okay. The next one is reproducible error. What's that about?
Reproducible error is basic testing to make sure that you can really reproduce the error, so that you've really identified what it is and then fix it. And if you can't reproduce it in the laboratory, okay, why not? Maybe you don't know precisely what it is. And so make sure that you can reproduce it. And so it's basic testing to be able to find that be sure that you really have the same error that occurs, so you know what the fault was, and then after you fix it, after you think you fix it, that you've really gotten it out of the system.
So it basically means first try to really nail the problem down before you, in a hurry, try to fix something.
Yes.
Okay.
Yes, that was a very good short summary.
Okay. Small patches is probably then the idea of just changing a little bit of the system instead of redelivering the whole big thing.
Right. And this will be governed by the tools and the languages and a whole bunch of other constraints upon your context. But smaller patches result in fewer hiding places for other faults, and fixing faults within patches is a well-known problem that is best avoided. The fix-on-fix problem.
Yeah. I mean, that's the whole point. If you just insert a small piece of patch here, then you don't necessarily know how it might affect the rest of the system. So you might change something that's actually incompatible with the rest of the system, creating new bugs or faults. Yeah.
Yep. But again, it's dependent upon your tools.
Yeah. But in any case, even if you just deliver a small patch, you probably have to retest, right?
That's right. And that gets to the reintegration pattern. The reintegration would discuss the test after you think you've installed your small patch to make sure that it was installed correctly and everything.
Yeah. Okay, the root cause analysis is the next pattern.
Again, you said this really early. Once we have an error, we want to fix the root cause. We don't want to fix just the symptoms. And the root cause, could be in many levels deep. And this is another place where the fault-tolerant mindset comes in. And one simple technique, which is what I write about in the book, is to ask a series of whys to, why did this happen?
Yeah.
And then you come up with the answer, well, why did that happen? And just keep answering a series of whys kind of until you get tired of it, or until you reach what you think is really the root cause of the problem, or the best level to fix it.
It's like a stack trace. And the last pattern of the section is revise procedure. It's probably then basically fixing a fault in the procedures if it's a fault in the operation of the system, I guess.
Right. Procedural errors account for a significant number of problems that are reported, like in the U.S. telephone network. And just because you've produced a procedure to help with reintegration, you should feel willing to make changes to it if it doesn't work. So it's possible that root cause analysis is going to point to some human error that was done somewhere, and it could be during the design and coding level. And so feel free to change those procedures and those methods also to make them more robust.
Yeah. Okay, this concludes our discussion of the patterns. That was really a long thing here. But I mean, now that we know the patterns, we don't necessarily know what to do with them. That's more or less always the problem with patterns. They give you a toolbox of, well, more or less little or big strategies of doing things, but there is still a big gap to making you an expert to fault-tolerant systems. And so one issue is how do you work with these patterns? How do you design and architect systems with these patterns? So do you have any recommendations there, what people actually do now, except for obviously buying and reading the book so they get more details?
And this is something I've been saying for a long time, and about the way to use patterns is I think the best way to use patterns, and these fault-tolerant patterns, or really any, is to become familiar with the patterns that are out there, and then when you're confronted with a design problem, you can say, oh yeah, I think I saw a pattern about that, and then you can go and find it and refresh your memory on what the things are.
Yeah.
And so become familiar with these patterns and the other patterns, and then when you're confronted with a new design problem, think about, okay, state. Where have I seen patterns about dealing with state and fault tolerance with regard to state? And so start thinking about the patterns in terms of your domain, problem domain. And you might think, oh, this system I'm building doesn't have any state that really gets saved, so I don't even need to pay attention to the checkpointing patterns.
Yeah.
And so you've got this big pool of patterns, like from this book and all the other books. And then when you come with a design problem, pull out those patterns that are most applicable and then start using them when you do your architecture and your design.
Yeah. One way I like to look at it, and the way that I talk about that with people, is that assume you're designing your system and you have this multi-dimensional design space. It's a big empty space initially, and this initial empty space is populated with some matter basically, and these are the patterns. They're basically like specific well-defined points in that n-dimensional space. So you wander around, you build your system, you talk about something, you've read a pattern, you get near this pattern, you basically gravitate to that pattern, you're now on that pattern. You think of how you can use that pattern. Is it sensible? Do I need to tweak the pattern a little bit? And if so, use it. And then just go on designing your system. And you might find more of these gravity sources of patterns as you go along.
Mm-hmm. Yes, that sounds really good. I haven't heard it that way, expressed that way before, but that sounds good.
Yeah, it's came up in discussions with people about patterns. It's nicely visual. So to conclude our discussion, why did you write this book? Well, obviously because you want systems to be more reliable, I guess, but wasn't there any material out there before?
No, that was the big disappointment, that there are a number of really good books about software reliability engineering, or there are a few books about software reliability techniques, but they don't really convey the range of solutions. There's some books that might focus on inversion programming or that kind of flavor of stuff, and then a whole lot of books that talk about doing the analysis and might have a little bit about some of the techniques. And so I was always looking on my bookshelf and never seeing the book that I wanted about that had the tips to help designers build fault-tolerant systems, not how to analyze them, but how to build them. And so that's the niche that I'm hoping to fulfill with this book.
Yeah, I mean, I've read several of your patterns before, since I'm obviously also quite involved in the patterns community, and I've always looked forward to seeing them in a book. So I really like this stuff. That's also why although I'm not building these kinds of systems, but as you said, everybody should have some of these things in their mind, because it just makes the toolbox of software architects and designers and developers a bit bigger with regard to certain very important points or some important aspects of software development. So I think it's a really interesting and good book, and I'm looking forward to read the printed version.
Good, thank you.
Then thank you very much for being on the show.
Well, you're very welcome. Thank you for inviting me.
No problem. Thanks. Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.